Thank you.
Thank you.
Thanks. Thank you.
So after the presentation, we'll send out a survey looking for comments to improvements, etc. on all these.
Topics of interest as well. Stuff that you guys are interested in getting trained on that help you out. Nobody knows you guys better than you know yourselves. I'm assuming you guys are gonna give me a thumbs up and we're ready to go.
Yeah.
So yeah, guys, as Mike said, this is kind of our first launch, and really what's important here is going to be the feedback from the field. You know, what type of training classes that we want to see in the future that's going to, you know, benefit everybody out in the field and make us be a little bit more, help us be more, you know, efficient and proficient in what we do. So your input is going to be greatly appreciated. Much better this way. Right?
Yeah, I'm glad we moved the table. We would have had a heck of a lot of people crammed into that one side of the room.
I'll make sure the guys over there are seeing already that part of the transition. Hey Carl, checking if you guys can see the video over there already. Awesome, you guys got the presentation? Yeah, if you refresh it, you should see on the other side of the screen that is blank, the notes, the new notes. yeah, I'll put the DVR so just in case. All right, no problem.
You got the sunshine right in the front of the camera now.
Yep, and actually we move it up from here because it will be over this side. How about that? Just be more careful when you open the door, please. Here you go. From now on, everybody is on recording. There's cameras everywhere, my friend. So.
Yep. You guys are the last one coming in the room here, George. How you doing, bro?
All right, so we are live now. We're live recording, everybody, so just keep that in mind. Again, welcome to our first installment of an FES Institute. We're trying to put a jolt in the system and get it started. This is going to be a basic electricity, so we're starting back from the basics. Did a survey of you guys before we came in today, and it seems like most people have already had a formal electricity class. So a lot of this will be review, but I'm hoping that everyone walks out of here with at least something new. So, without further delay, today we're going to cover introduction to electricity. We're just getting down to the nitty-gritty basics, atomic theory. We're going to talk about atoms, electrons, protons, neutrons, etc. Properties of electricity. We're going to cover resistance, voltage, and current. Cover Ohm's law. Jump into Watt's law briefly. Cover symbols so that we can start looking at circuits. And then we're going to cover electrical circuits. And we scratched electrical diagrams today. We're going to cover electrical safety. Safety on the work site. So this is always the toughest question that I ever ask. We work with electricity all the time, but if I were to ask you, what is electricity? Who actually thinks they have a good answer? That's usually what I get. Go ahead, what you got?
It's a form of energy.
Okay, that's pretty good right there in itself. So a form of energy. Everybody usually goes to electrons moving center to center. Electricity is just a form of energy, which is the result from existence of charged particles, either statically or accumulated dynamically as a charge. That just means static electricity. Charge is built up on an object, that's static electricity. Dynamically would be electricity flowing through a conductor. So electricity is just a form of energy, just like heat. Atomic theory, when we start talking about electricity, getting down into the very basics of it, go down to a basic simple atom. Pretty sure that's a lithium atom. So every atom has nucleus and one or more electrons bound to the nucleus. The nucleus is composed of protons, which has positive charged particles, and relatively speaking with the atom, the protons have weight. The nucleus also has neutrons, and neutrons have no charge. And neutrons also have measurable weight. Orbiting the nucleus are what's called orbital shells, or electrons are on the orbital shells. So electrons are negatively charged particles. In relation to the atom, they have negligible weight, meaning you can't weigh them. And they orbit the nucleus. They're constantly on a pattern, just like your planets circle the sun. Orbital shells, starting from the inside out, are lettered. They all have standards. KL through Q. Starting from the innermost, we go in that direction. Basically what we want to pick up from this slide is that the only thing, when we're talking about electricity, the only shell that matters is the outside shell, the valence shell. So the valence shell is what has your free electrons, and your free electrons are going to migrate from atom to atom. And when that happens, that actual phenomenon of electrons moving from atom to atom, that in itself is electricity. So again, electrons on the valence shell, which are furthest from the nucleus, are more loosely bonded to the electron, or to the atom. So those electrons can move from atom to atom. If an electron is affected by an outside source, it becomes a free electron. That electron is now looking for somewhere to attach itself to. Once it leaves the electron, it's affected the charge, and that makes that atom a positive ion. So we have positive ions and negative ions. Positive ion is an atom that has lost an electron. It now has a more positive charge. And a negative ion is an atom that has gained an electron. So it has an extra electron, creating an extra positive charge. Here we're going to see the process actually in effect. So we've got two lithium atoms. Both have 3 protons, 3 neutrons, and 3 electrons, which means they both have a neutral charge. They all equal out. I'm going to knock that camera over. I missed the slide there. There we go. So now we have one electron jump to the other, and when that happened, we've affected the charge of the 2 atoms. We've now created a positive ion, stop touching the screen, and a negative ion. Conductors and insulators are just describing the different types of materials that we work with. The conductors are atoms which have fewer electrons in their valence shell, which means they have more room to pick up extra electrons. As the name implies, conductors are conducive to allowing electricity to travel, so they give you a path for electricity. And what makes the conductor better is the number of spaces available in the valence shell. So as we go farther out on valence shells, or orbital shells, remember the last one is always the valence, we pick up more room to actually have more electrons, so each shell can hold more as well, and that will also make a better conductor. Here we have a neon atom, which is actually an insulator. My slide jumped ahead on me. Insulators, let me go back one and forward. Insulators are atoms which have more electrons in their outside shell. So this atom has an abundance of electrons. So if we had a free electron like we saw before that was floating around and trying to come over, there's no room for it on this one. So this is a good conductor. That electron cannot touch it. Hit the screen again. So we'll jump right on over to semiconductors. We've talked about conductors and insulators. Conductors will allow electricity to pass. Insulators prevent electricity from passing. Now, every insulator can be overcome with enough pressure. We'll talk about that later when we get into voltage. So insulators are good to block electricity, but keep in mind that you can overcome an insulator with enough pressure. Semiconductors are unique. There's only really 3 of them that are common. They have 4 electrons in their valence shell, and we basically affect the continuity of semiconductors by applying voltage to them. Carbon and silicon are the 2 most common, but again, semiconductors are too complicated for this course. We'll cover them later on. If this is a blown up wire with jacketed, and we cut the jacket back, basically what we see here is a wire that has filled with tiny little atoms inside. So one pinhead on a needle has 5 million, or basically 5 trillion atoms. If you think about how much is stored right there on the tip of that needle, and then how many you have on this path on this conductor. Every one of those atoms has free electrons. Those are electrons that are removed for the electricity. So when this wire becomes energized, it's basically pressurized with electricity. Voltage is pressure. It's looking for somewhere to go, just like water would. When you have pressure in a water system, it wants somewhere to go. When you create a pinhole in that pressurized vessel, it shoots out. Electricity will do the same thing. So we're using this insulated jacket to streamline the flow of the electrons. Properties. So that's atomic theory. I didn't want to spend a whole lot of time on atomic theory, mostly because when you're out there on the job, you're not really thinking about atomic theory. And secondly, I knew that a lot of you already had a formal class. So let's move on. Electrical pressure, current, resistance. Where you're actually going to start to have useful knowledge that you'll use every day in the field, or at least most days. So electrical pressure is a measurement of energy potential present within a conductor and stored within a power source. We measure electrical pressure in volts. Electrical current is a measure of energy flow presented along a conductor. We measure electrical current in amps or amperes. And electrical resistance is a measure of the opposition of current flow. And we measure resistance in ohms. I'm going to jump back to my wire slide and just cover resistance one more time. So when we say an opposition to current flow, we talked a moment ago where I talked about all of these little atoms that are filled on this wire, right? Actually got to make spots. So this thing is filled with millions and millions and billions and trillions of them. Resistance is basically when you have those free electrons. Let's say this is a free electron. This thing is really packed solid with atoms, right? There's millions of them in there. We just covered it. These electrons are trying to move through all this. And while they're banging up against all those atoms, that's actually what you're getting in resistance. That's what your resistance truly is the resistance of the electrons passing by and jumping on and off all those atoms. Does that make sense? All right, I know everybody, most people have seen this picture. This shows you the properties of electricity in a visual format. So we're looking at volts. I keep saying volts is pressure, right? So in this picture, you got volts here. Volts is trying to kick amps in the rear, right? It's pressure pushing it through the hole. Amps is your actual flow. It's a measurement of how much is going through, right? You can physically see amps and measure it. And ohms is the resistance. It's trying to tighten down on the hole and stop the electricity from passing through. I'm going to go through them again. So voltage is electrical pressure. And it's basically the difference in electrostatic potential between 2 points. The base unit of measure for voltage is the volt. The letter is the V symbol. And then I gave you a few examples down here just to show you volts, millivolts, kilovolts. So to go between them, you just multiply by 100, well, 1,000. Yeah. Okay, that's right. I was just spelling it out. I thought I did a conversion there. Voltage is sometimes referred to as potential, and this is because it really is the potential. It's the potential to do electromechanical work. So voltage in some cases is referred to as electromotive force, or EMF. So you have electromagnetic force and electromotive force. So voltage is electromotive force. Unfortunately, they're both called EMF. So if someone says EMF, you gotta ask them which one they're talking about. This is just some extra info. I don't expect you to realize or maintain it, but a volt is really an expression of the work per column. And a column is equal to this many electrons. I'm not even going to try to say that number. So this is all ironed out specific science. Someone can actually sit down and calculate how many electrons are flowing, but it's all specifically laid out in science, and you can calculate everything that we would normally see in the field. Before I said voltage is the difference between two electrostatic points. In this diagram, if we were to measure the voltage from here to here, that difference in potential would be our voltage. One side would have one voltage, one side would be the other voltage. It might not necessarily be zero, but the difference between the two is our potential. Amperage. Electrical current is expressed in amperage. Amperage is a measure of electrical flow. The base unit is the amp. We use the letter A to signify amps. There's your same scale for amps, regular amps, kiloamps, milliamps. Ampere is equal to the flow of one column. So we talked about the column in the last slide, basically with the volt and the work performed with 1 volt, or 1 column. So the amp actually is the column. That is the measurement for the amp. Electrical resistance is expressed in ohms. Ohms is a measurement of the resistance to the flow of electricity. We just talked about that when I brought the wire back up. The omega symbol is the signal for ohms. It's that right here. And then an ohm is an expression of the resistance in a circuit, which is producing 1 amp of current when applied to an electrical difference of 1 volt. So that's how they actually scientifically measure an ohm and verify it when they're creating equipment. They know that 1 ohm, you take 1 volt and apply it to a load and you get 1 amp, that is equal to 1 ohm. All right, we're going to relate electrical systems to hydronic systems. We work with mechanical systems every day. This will give you a good visual idea of how the systems work. I'll move over to my notes for a moment. So we're looking at a tank of water. It's got a gate valve and an open-ended pipe. With the gate valve closed, the valve acts as a switch, or it breaks the path of flow. Completed flow, we get amperage. We break it, then we get no flow. The tank standing is a standing column of water. So a standing column of water has pressure, right? As we increase the height of that column, the pressure on the bottom increases as well, right? Same thing with voltage. So as the water itself moves through the pipe, it creates current. Next slide, showing pressure over time, and we're going to replace that with voltage. And then current flow out of the bottom. I should have been sliding through the slides I was talking. So when we open the valve, reducing the resistance, the pressure, we begin to push water through the valve and out of the opening of the pipe. What can we do to increase the amount of flow through this pipe in its current situation? We want to increase the flow through the pipe. What can we do? Anybody?
Reduce the resistance.
Reduce the resistance, okay? Thank you. That's what I was looking for first. All right, so we reduce the resistance and we get more flow. We have the same standing pressure, but we reduce the resistance leaving the pipe, so we get more flow. All right, this is back to the same as we were before. We got limited resistance, but I want to get more flow again. What else could I do?
Increase the pressure.
Increase the pressure, right. So we increase the pressure, we get more standing pressure, more voltage, we get more current. Increase the pressure and decrease the resistance. We see here I've opened the valve. Now we have the most current, all right? High pressure, low resistance, most current. Go back and look at a couple more. So now we're going to go into, we still have our high pressure, low resistance. We close the valve off. This is the first time we've seen high pressure, high resistance, which results in more current than we have with low pressure, high resistance, but not as much as we do with high pressure, low resistance. Stop saying high pressure, low pressure resistance so much. All right, so we reduce the voltage and the flow reduces even more. By maintaining the same voltage but decreasing the ohms, we're able to increase the amps again. So, in this scenario, I don't have a slide for this, but if I drain this tank all the way down and I reduce the difference in pressure across the system, theoretically we stop moving water, right? If there's no pressure to push the water, then we stop moving the water. Same thing happens in electricity. You remove the pressure, you stop moving electrons. So hopefully by this time you're already picking up the relationship between an increase in voltage, an increase in resistance, and it definitely has some effect on the amount of current that's produced. So let's start talking about Ohm's law. Ohm's law states that the current going through a conductor between 2 points is directly proportional to the voltage across the 2 points. And here I give you the cheat sheet for Ohm's law. See, I is current, E is voltage, and R is resistance. And everyone has probably seen this picture before. If we have 2 of the 3 variables, we can always solve for the third. So if we have amperage, which is I, and resistance, which is R, you cover E, I times R will give you E. E over I will give you R, and E over R will give you I. So we're solving for voltage, we're looking for E. What are we going to do? We're going to cover E, right? E, I times R equals E. Looking for amperage, cover up amperage. I equals E over R. Looking for ohms, we're going to cover up resistance. R equals E over I. All right, so this is time for you guys. We have a light bulb that has 120 volt differential in potential. We measured a resistance of 240 ohms across the bulb. How many amps are we moving? Ohm's law right there on the screen. 120 volts, 240 ohms. What's 120 over 240? 45. It's half, right? 1 over 2. 120 goes into 240 twice. It's all written right up here, guys.
Frank,
Yes.
the guys over there, I was asking if you can speak a little bit louder because they
Speak
cannot
louder,
hear you.
sure. I'll do my best. Here's our math. So I equals E over R, I equals 120 over 240. I turns out to be half an amp. Change it up. 24 volts, 0.25 amps. So I'm looking for resistance now. Got 24 volts, 0.25 amps. How much is my resistance? What's my R?
$96.
96. 24 over 0.25 is 96 ohms. I don't mind if you use a calculator if you need to. In fact, the very last one we do, I know you'll need it. All right, last one we're going to do. for Ohm's law here. 369 ohms, so we have R, 0.75 amps. Anybody?
276.75.
277. This is one leg of a 3-phase circuit. Or one leg of 3-phase power. So we got 277 volts, 369 ohms, we're pulling 3/4 of an amp. Could be something like a contactor, something similar to that. 0.75 amps out of a contactor so much.
It's a light ballast.
There you go, I don't deal with lights. All right, this one's gonna be practical application. You guys are actually gonna be able to use this in the field. So in this situation, I'm looking for I. I have 1 volt and 250 ohms. What's my I? Somebody use a calculator, tell me. .004, you guys are live today. 0.004 amps is what? 4 milliamps. So in this situation, we got 4 milliamps moving through the circuit. If we put in a 250 ohm resistor, we can convert that 4 milliamps to 1 volt, right? So you just converted a 420 milliamp signal down using a 250 ohm resistor. 5 volts. We get 0.02 amps, and 0.02 amps is equal to 20 milliamps. So there you go. Full circle. 2 to 10 volt. Same thing. We double the resistor, so we double our voltages. But we get the same result. Why would we want to use? Which one would you use if you were in the field and you had the opportunity?
0 to 10.
Okay. Don't have 0 to 10 on my options with 420 output.
500 ohms.
Between these two, which two would you use? 1 to 5 or 2 to 10? If you could use either one, which one would you use?
2 to 10.
2 to 10. Why?
More resolution.
Shot more resolution. Yeah. There's more room to have more units in between. Ohm's law. We're going to be hitting Ohm's law on and off throughout the rest of this slide. But as far as picking up on Ohm's law, I expect everybody to already know E over I times R. Watt's law is very easy, much easier than Ohm's. Watt's law is just watts equals volts times amps. So your power equals your electromotive force, there we go again, EMF times your current. That equals power. Back to our 120 volt light with our 240 ohm load. We said it had half an amp, right?
Mm-hmm.
So how much power is this ball pulling? Here's your formula. Power equals volts times amps. We know the volts is 120, and we know the amps is 0.5.
Six.
60-watt ball. When you start getting into Watt's law, I don't have all this memorized, I'll be completely honest with you. So you can find that pretty quick either with your phone or just take a picture of it. So what this wheel pretty much shows you is that with any two of the four, so you got P, R, I, and E, power, voltage, amperage, and resistance. So with any two, you can find the third one you're looking for. Doesn't matter. There's the one that we just did, so you can use this as an example. We got 120, come right here, we just did power. 120 squared over our resistance, which was 240. So 120 squared is that right? 14,400
Yeah.
over 240. Yeah, well, I pretty much know the answer is 60 because we already did it. Again, any two you can solve for the other one, or in whichever you're looking for. That was interesting. That's it for Watt's law. We start to couple symbols so we can get into circuits. All right, symbols. Conductors. This is an either-or situation. So when you're looking at a diagram, if you see your junctions have dots on them, there's a pretty good chance that your crosses mean that they don't actually touch. There's no connection there. If you see with a jump over top or the camel hump, then this is your junction and this is your crossing. Here we got a DC power source. Remember to stop touching the screen. So basically it's a battery. AC power source or a generator. Fuses. Both symbols are both fuses. Circuit breaker. This is your ground connection. Switches, single pole, double throw. Single pole, single throw. Single means that there's one pole and it's got one way to move. Single pole, single throw. Single pole, double throw. One switch, but it's got two positions. Double throw. Throw one, throw two. Contacts. Normally open, normally closed. What do we mean by normally open, normally closed? And it's resting position. Thanks, Chuck. Resistor. So resting position when it's de-energized. That's what we mean by normally open, normally closed. Normal means if it's sitting there, not doing anything, not in its normal state. And we have resistors and coils, which are kind of the same thing, but not really. They are both loads. Turn that off. There we go. So these two are the only ones that are loads out of all your symbols. What's that make everything else? We got, well, except for these two. These two are power sources. So everything else has to be a conductor, right? It's not a load, it's not a power source, it's going to be a conductor. Simple circuits. Simple circuit just means it's a circuit that has power source, a load, and conductors. Those are the bare minimum, the three that you need to make a circuit. Missing any one of them, you're not doing any work. So this is the most basic of circuits. This is from a DC power source. So before I said this, a DC power source is similar to a battery. So now that we start talking about DC and AC, we haven't covered any current yet. Let's still talk about the differences in current. There's two types of current when dealing with electricity, DC current and AC current. DC is direct current, meaning it flows in one direction. AC is alternating current, meaning it alternates back and forth. Cover those in more depth now. So in this circuit, we've got a 9-volt DC power supply, pretty much a 9-volt battery, and a resistance of 36 ohms. So the DC power supply, for any DC power supply, the flow of charge, this is where it gets confusing for some people. When we say current, the flow of charge is actually from positive to negative. But the actual physical process that's happening is electrons are leaving the negative terminal and traveling towards the positive terminal. Now, to help that, the reason that happens, the flow has to go this way for electrons because this side's already positively charged. So if anything negative gets near it, if anything positive were near it, it would be repelled. But since it's negative, it's attracted, right? For something from this side to go to this side, it would have to be a positive entity, right? For something positive to be attracted to the negative and actually move there, we have to have something that's actually positively charged move. Can that happen? What's positively charged? The protons in the nucleus, right? The protons in the nucleus, do they move or are they stationary? They're stationary, so they're stuck here. So the only thing that can move are all those free electrons that are over here making this side negatively charged. So once you close that switch, you now have electron flow from negative to positive. Hopefully that helped understand why it functions that way. This is the same thing I just talked about. So a negative terminal holds a negative charge due to an abundance of negatively charged ions, or atoms which have extra electrons in their valence shell. A positive terminal has an abundance of positively charged ions, which are missing electrons from their valence shell. When the circuit completes, the electrons flow from negative to positive. Just like this. Circuit's closed, electron flow. Alright, so just like the name implies, direct current flows in one direction, from positive to negative. How much current's flowing in this diagram? Got 9 volts, 36 ohms. I even put your ohms all back up there. I'm sorry? Somebody said something.
0.3.
0.3?
0.25.
0.25, we're back to a quarter amp?
Yep.
Oh, look at that, I got it on there already. 0.25 amps. Not sure that. Pardon me a moment, let me get rid of that menu. All right. Same circuit, just plug in different numbers. So again, 120 volts DC, we're looking at 144 ohms. How much current's flowing? 0.833 amps. So 120 over 144 is 0.833. Seems odd now, but it's going to work out later. Again, this is DC circuit, and we said DC is moving in one direction, right? Constantly flowing in one direction. So if we plotted DC power, or DC current, on this diagram that has voltage potential shown here, and time elapsed on the x-axis, what do you think our plot's going to look like? Saw somebody motioning that's going to go up and down, almost in like a rectangular pattern. Anybody else? No? Okay, so DC power, if we think about it, let's say it's a 9-volt battery, and I have 9 volts right here.
It's gonna stay there for the duration.
Is it not gonna just go across? If it goes down, what's that mean?
It's off.
It means the voltage is dropping right here in these spots, doesn't it? I was close. That's what our plot looks like. We have 9 volts. When do we have 9 volts? All the time. Now eventually, over time, if this is a battery, true battery, what's this line gonna start to do? It's gonna start to drift down until the potential between the positive and negative terminal have equalized, at which point we no longer have a difference in pressure, so we stop moving electrons. Time to recharge the batteries. Direct current, recapping it up. We know it moves in one direction, it flows from negative to positive, has constant, consistent voltage polarity. Everybody understand those three? And everybody agree? Okay. Alternating current. AC stands for alternating current. Rather than flowing in a constant direction, pole to pole, like DC circuits, the flow of charge in an AC circuit is rapidly changing back and forth, or it's alternating. Just like so. You see it changes back and forth rapidly. Here in the US and Canada, I'll throw this on, we have our power at a peak frequency of 60 hertz. And then what that means is it changes that back and forth, just like you see here, 60 times per second. So it changes potential 60 times per second. If we were to plot alternating current, it looks a lot different. as we talked about, our voltage potential changes 60 times per second. So basically, as time goes on and our voltage changes, if you think about, if we start at 0 degrees and we make it to 120 degrees, and we make it back to 0, and then back to 120, that's almost like going in a full circle, right? We start at 0, and we go back to 0. So if we were to try to draw this circle right here, now we start to go back in time, right? Instead of going back in time, we're going to keep going with time and bring our circle back. That's where you get your AC sine wave. So basically this is your 90 degree, 80 degree, 270, and 360 of your circle. And right here, we pass 1/60th of a second. So it's time to start our process over again. And then we go back. Somebody just fell out.
Fall asleep.
We're going to see it moving here in a brief moment. I know it's going to start. So I'm going to turn power back on. This is what it looks like as it's passing through time. We can see our voltage potential is constantly changing. We're at negative 120, coming back to 0, off to positive 120, coming back down. All the while, this is time now. So this is, we're constantly moving through. This is into the future. 1/60th of a second, that's what it would be. Does that make sense? Everybody following how that works and how the pressure changes back and forth? We'll cover how it's actually generated in another class. This is a really good example or analogy of what we're looking at. Voltage, electrical versus water-based systems. So this pipe is actually filled with water. It's got a little piston in it. And as this generator moves, it's moving water up through the resistance, and then it goes back down and moves water back. Same thing that's happening in AC power. We're constantly moving charge back and forth through the resistor. All right, so this is the same numbers that we had on our DC circuit, 240 and 144. So Ohm's law applies the same to both AC and DC. That's all we're beating home on this slide. We've got the same exact numbers, 0.833 amps. So how much wattage is that bulb using? 0.833 amps. 100 watts. Did you do that with a calculator? Or did you double the voltage and then divide it by the resistance? Well, not double, but. So we did this one earlier. The easiest way to figure this one out is 120 times 120 equals 14400 over 144 ohms comes out to 100 watts. So that's a 100 watt bulb. Am I following that? We're doing plenty of examples of how to use Ohm's law. I know this seems boring, but you don't know how many times I've been out in the field and actually used Ohm's law. We'll get into examples of that in a moment too. Again, just keep your mouth shut and keep pushing the button and it'll come up there for you. All right, so now we're going to start to get into more complex circuits. So far we've been looking at simple circuits. Simple circuits have one load. We get into multiple load circuits, we're going to be dealing with series and parallel circuits. We'll start with series. The characteristics of a series circuit, the current is the same at all points in the circuit. So what we mean there is that if I take a current reading right here, and it's reading 2 amps, and I take a current reading right here, or right here, or right here, or here, or here, or here. Doesn't matter where I take it. What's my reading going to be?
2 amps.
2 amps. Current is the same everywhere in a series circuit. The total resistance, next point, is equal to the sum of all resistances. So, if this were 3 ohms, and this were 3 ohms, my total resistance is 6 ohms. There we go. And the other 2 or 3 are actually grayed out, because as long as you know these two, and you know Ohm's law, You don't need to remember those, you'll figure it out. So the voltage across the entire circuit is equal to the sum of the voltage across the drop of each individual load. What I mean there is, if we were to, use an eraser, if we were to measure the voltage potential between here and here, what would my reading be? Point A to point B with 120 volts. Anybody?
120.
120 volts, that's it, the full potential. So we're reading across the entire load, and we're reading from one side of the power source to the other. So it's gotta be 120. So what that statement says, the voltage across the entire circuit is equal to the voltage drop across each individual load. Before I set these to both 3 ohms. So I know that my voltage drop is going to be 60 because I cut it in half. Those resistors are the same size. But if they were different, if this one were 6 and this one were 3, my voltage drop between the 2 resistors is going to be different. If I read from here to here, I'll have 120 volts. But if I read from here to here, I will not. Does anybody know what I will? 80. So how do you figure that out? Who said 80, by the way? Matt?
There's Matt behind you too.
George pointed to Matt, which like he threw one of the bus. It was him, wasn't me? Stop looking at me. So instead of actually figuring out what the resistance and flow is, once we're in a series circuit, you can do it proportionally. So we can take the full number of 9 and then figure out what 6 and 3 are proportionally. And I'm pretty sure that's what they did. So what's that about?
2/3.
2/3. So 2/3 of 120 volts is 80 volts. You can figure it out precisely, but we're not at that slide yet. So the voltage drop of each individual load is proportional to the resistance of the load, which is exactly what we just talked about. So if we knew that we had a 6 and a 3, then it's proportional. 3 and 3 was easy, we just split it in half. Those numbers are also going to yield you some very high current draw. All right, characteristics of a series circuit. I left them up there. We're going to do some examples now. I believe that's where we're at. My examples were to actually draw them in myself. So we just did a couple there. We did 3 and 3. So let's say I have a 18 volt source. That's a weird one. And 9 ohms and 9 ohms. My total resistance is 18 ohms, right? 9 plus 9. So what's my amperage?
1 amp.
1 amp. There we go. 18 over 18 1. Trying to make it easy. If we were to come down here and we did 3, 3, and 3 with 36 volts. Now what's my current draw? What's the steps to figure it out, right? Take these and add them together, we get 9. We take 36 over 9, we end up with 4 amps, right? Series circuits aren't too bad, they're fairly easy because you're just adding the stuff together. The hardest part about a series circuit is to figure out what the voltage drop is. And again, it's proportional to the loads. Does anybody want to keep doing any more examples on series circuits? Did not think so. Parallel circuits. These are the ones that you guys are going to run into the most. We don't really think about it, but they are. There's a typical parallel circuit, and a lot of times you'll see switches in here, or what you might see is this diagram inverted, and some of these go into a common point on the controller, with the controller breaking the rest of the circuit going out. Controller is just connected to a bunch of parallel circuits, using the same power source, different lengths. So in a parallel circuit, the voltage is applied equally across all the loads in the circuit. And what that means is that, again, if we have a 120 volt power source, and I check my voltage from here to here, it's 120 volts. If I check it from here to here, it's 120 volts. So the voltage is applied equally across all the loads. So they all get the same full potential. All right, no, that's not gonna work. The total current is equal to the sum of all the currents for each load. So once we know that we have the same potential on all the loads, and we know the resistance of each load, we can figure out the current of each load, and Ohm's law applies as it should. The total resistance is always less than the resistance of the smallest load. That's the one that most people have trouble with. So, if this were 120, and this were 50 ohms, and this were 100 ohms, what would my resistance be? Ballpark it. More than less than 50? Less. Who says it's going to be more? Let's say I have this. It's a 100 ohm circuit. 120 volts, part of my chicken scratch. I got a 100 ohm circuit, right? I'm going to add more resistance. You might think, I add another resistor. Did I increase the resistance of the circuit, or did I decrease the resistance of the circuit?
Stay the same.
Stayed the same? So, in this case, I'm going to transfer this up here, and that's exactly why I'm going through this. So we had 100 ohms, and let's pretend that that top wire is not up there. So that's what I drew down there at first. So what I said, I was going to go back, and I'm going to add another load to the system. I'm going to put in another resistor. And even though I did that, I added another resistor the same size. I didn't increase the resistance, but I also didn't keep it the same.
That decreased.
I decreased it, because in reality, no matter what type of resistance I put in here, it's still another path for electrons to flow, right? So as long as I've added another path, that's another place that they can go, independent of how many can flow through here. So it's got to be a lower total resistance. Make sense? Even though we've added resistance, we've also added another path. So again, the total resistance, doesn't matter how many loads you have, the total resistance of your circuit will always be less than the smallest load. I need a quick button to erase the whole screen. All right, we'll do some parallels real quick. And I think I'm supposed to write these in too. Check. So in this case, I'm just going to keep it easy. Can you take one of those and pass them around? There's some papers coming around that have some blank circuits on them if you guys want to actually pencil them in and take some scratch notes. So let's just say 6 and 6, and then on this side we'll do 12, 8, 9, So when we talk about series circuits and calculating the total resistance for a series circuit, it was pretty easy, right? All we did is just added up the loads on that path, or that conductor, and the total of the loads was our total resistance. But as we discussed a moment ago, when we added another pathway on a parallel circuit, we actually decreased the resistance. So the formula to figure out total resistance on parallel is a little bit different. And that formula is over here. So the formula for total resistance on a parallel circuit, there is a shortcut when you're working with just two, but I find that if you just remember the full formula, your life will be a lot easier down the road. So RT equals 1 over R1. If you just remember that part, you're golden. RT equals 1 over R1. If you can make it there, all you need to do is just add the other loads. Plus 1 over R3, etc., just like we have here. So what that's saying is RT equals 1 over 6 plus 1 over 6. Somebody help me out. I know you got a calculator. I just picked these numbers out of nowhere.
0.16.
So that's 0.16. Okay. So
0.16 would be.
RT equals 0.16.
Or no, the total is 3. I'm saying one
Oh.
reciprocal of 6
Okay,
is
gotcha,
1.16.
gotcha. Thank you.
Yeah. And they're the same as, if they're the same in a parallel, it's always half.
In this situation, what's really happening right here? If we take this, well, we add this, we get 2/6, right? Which is just 1/3. And 1 over 1/3 over 1/3 is no different than 1 over 1 times 3 over 1, which equals 3, right? So in that case, we end up with a total resistance of 3 ohms. We didn't really need to do the math to figure that out. We knew we cut it in half by adding the same one in. But 3 ohms, we're gonna end up with how high of a wire? How many amps?
A lot.
40 amps. Pretty good sized circuit for 120 volts. If I follow how we did that using the formula, that's the most important thing we're trying to beat in on this slide, is using that formula to do total resistance. Once you got total resistance, you just apply Ohm's law. So on this one, RT equals 1 over 12 plus 1 over 18 plus 1 over 24. I gave myself easy numbers to look at. Is everybody on top of this one already?
Your thumb, that's.
How much? I think it might just be just the corner.
Oh,
So
the
if it's
corner.
not a full flat surface, then it
Oh.
doesn't do the eraser. If you accidentally brush it with the corner. So really, I don't even need this.
Just draw with the eraser.
Yeah, so I think we had 40 and 40, and then 120. I know you guys are working on the other one, I'm just putting another one up there real quick. Anybody have an answer for this one?
10.27
Is the total resistance?
total resistance.
10.27, I'm gonna take his word for it.
Or
So then we end up with, well, I think I said it was 120. Close to 12 amps, somewhere around there, we ballpark it. These will work out actually for you much better. So go ahead and do those two real quick. And we'll go over them. I can tell you right off the bat, if you haven't even started to put it together yet, I'm sure you have. Anytime you're working with a parallel circuit that's only got 2 loads and both resistors are the same, you just cut the resistance in half. So those two 40s come down to a 20 total. got RT equals 1 over 100, 1 over 50, 1 over 300, which converts into 3 over 100 plus, what was that, 50? 6 over 100. Whoops, that should be 300, 300. And then 1 over 300, which turns into 10 over 300, or 1/30th. And 1 over 1/30th equals 30 ohms total resistance. Everybody come up with that?
Yep.
Or 4 amps. All right?
I think we should have started with the basic algebra class.
That's why I try to write it out, to help you guys out in seeing the conversions, because I know it's been a while since a lot of people have actually done that, making common denominators and stuff like that. All right, well, on this one, I want you to tell me what size fuse I need. So calculate your current draw, figure out the total amperage, multiply by 125, go to the next size up for your fuse. What size fuse do I need?
Easier. You guys have a
For-
scientific calculator on your
for-
iPhones if you go
Yes.
portrait
When you're
mode.
looking for that, I've been talking
And
with
then
the
you can
guys
use
over
the
there.
reciprocal button
and,
instead of dividing.
They're on the class over there. They want to share a picture with you. They're paying attention over there and working out.
Man, so they're seeing all the times.
I'll show you later. That's the group on the other side, guys. So everybody on it.
All right, so we're down to the last simplification part. We got 1 over 57 over 900, which turns out to be about 15.78 ohms.
Yeah.
I just know how to get the calculator. I'm gonna get confused.
So that puts us at, remember we're at 24 volts here, not 120.
So I gotta use like the columns.
It's gonna put us at about 1.52? 1.52 amps times 125% would take us to 1.9. We're looking for a 2 amp fuse to protect this circuit, right? And notice I said we're looking for a 2 amp fuse to protect this circuit. We're getting ready to get into electrical safety. That 2 amp fuse is not there to protect you. Remember that. Fuse and the circuit protection, circuit breakers are in place to protect the equipment and prevent fire. They are not there to protect you. You are there to protect yourself. So make sure you act safely. We're going to cover on how you do that next. There's a pretty good chance you'll be laying on the floor by the time that fuse blows. 2, round it up, 2 amp. All right, combination circuits, before we get into electrical safety, we'll try to cover these briefly. Not quite sure how I'm doing on time. But combination circuits are a different beast. So a lot of people get nervous with them, but there's really nothing to be nervous about. Again, all you need to know is Ohm's law. So when we run into a combination circuit, such as this one, you see that we have a parallel circuit,
And then the voltage and current.
and we also have another series load. So here, we have 2 parallels that are in series with each other, and then this last one is a really different one. We got a parallel into a series that then form 2 larger parallels. Am I follow that? So we're going to break each one of those down and then apply Ohm's law to it. How am I doing on time?
It's 440.
440, thank you. Sorry about that. Come on. All right, so as I just discussed, the process for breaking this down. So we got a parallel circuit here, which is load 1 in this series. Then this second load is the second load in the series circuit. So that's load 1, that's load 2. We're going to isolate those. We're going to calculate the total resistance of this circuit. So let's just say that this was 6 ohms and 6 ohms. Total resistance for this circuit is 3 ohms. Then we're going to calculate the total resistance of the entire circuit using Ohm's law. At this point, I should have already had 3 ohms over there. So at that point, I'm back to total resistance of 6 ohms, that's right. Because these 2 in parallel equal 3 total, and then they're in series with another 3 ohm load, which equals 6 total. The last thing you want to do is to use the current, because now that we have the total resistance, we can figure out what the current is at these points, right? The total current for the load. And once we have the current, we can take the current and the resistance and find out what the voltage drop is across each load. Let's see if I have an example coming up. Nope, I picked them to do out of our head. So, in the interest of saving time, we're going to focus on one. So which one would you like to do? A, B, or C? A it is. All right, so we'll try to make it easy. I think if I do 24, that's 24. 9, nope. Yeah, let's do that. Oh, I don't want to do that. I'll give me that. Let's see what this comes out to be. All right, so the first thing we were going to do is total resistance of the parallel circuit. What's my total resistance of the parallel circuit?
6.
6. It's 2 of the same. Over here I have 18, my total resistance of the entire circuit, 24 ohms. 24. So we end up with 1 amp total, right? Now I want to go back and figure out how much resistance is flowing through. I made it easy on this one. So again, we get to the parallel circuit. It's proportional to the resistance. So on this, our proportion is 50-50, right? 12 and 12. So I couldn't have made it easier. We know that I have 0.5 amps running through here, and 0.5 amps running through here. You can take your meter and verify that. Now, if those were different voltage or different resistances, then we would come up with a different amount of amp draws through those 2 circuits. That's your homework. You guys can handle that when you're in. All right, so we've covered all the way up to this point. And now we're gonna cover electrical safety. Using safe work practices while working around live electrical circuits. Electrical safe work practices are procedures established to protect workers from electrical shock and arc flash hazards when working with or near sources of electricity or tools and power equipment provided by electricity. Straight from OSHA's slideshow. Lockout tagout is a method of controlling hazardous energy during the servicing or maintenance of machines, power tools, and equipment. Types of energy that generate hazards in the mechanical construction industry are electrical, which is what we're covering today, mechanical, thermal, pneumatic, and chemical. So for a few of those, at least 4 of those, you will probably have to lock out an electrical source to protect yourself from the other sources of energy. Mechanical runs off electrical. Thermal runs off sometimes electrical. Pneumatic runs off electrical. Lockout sources are uncontrolled energy, so they cannot be unexpectedly. Lockout sources, let me start that over. Lockout sources are uncontrolled energy, so they cannot be unexpectedly released when servicing or performing repairs or maintenance work on machines, power tools, or equipment. On rare occasions where it is not possible to use a lockout device, use an appropriate warning tag in place. So everyone should have lockout tag out equipment on their trucks. I'm sure that they do. And when we access a disconnect or a unit, you should be locking out the unit, turning off the power and locking it out. Before you start any work around energized equipment or live electrical circuits, verify your voltmeter is functional. Before you even start the work, take your voltmeter, go to something that you know is functional, and test your meter and make sure it works. Don't turn off the breaker and then go in and check the disconnect. What if your meter is messing up? So, in that case, you might get a bad reading, and you go put your hands in there, and next thing you know, you're laying on the ground. They don't find it until the next morning. So always check your meter before you even go to check the source you're going to work on. Then perform your lockout tagout procedure. Use your voltmeter again to verify the equipment is dead before you start putting your hands in it. Perform your work to be completed. Double check your work and workspace for safety. Not just that you did the work right, but that you didn't leave things in there that might blow up. Something that might short out the circuit. And of course, make sure that you did your work right. Remove your lockout tagout and verify the equipment's functional again. So how to properly use your voltmeter. Just having a voltmeter is not good enough unless you know how to use it. All right, it's not going to protect you unless you know what you're looking at. So, with your voltmeter on volts, what am I going to read right here? 120 volts, right? I'm reading the full differential potential from my power source with no breaks or loads in between. So I get full potential. 120 volts. What am I going to get if I read right here? It's okay to say the same. 120, because in theory, or not theory, in reality, I'm reading a conductor that's connected to my power source with no obstruction between, and on the other side, I'm reading the other side of the same power source. So even though I'm on this load and this load, my potential is still 120. So I gotta remember that the answer comes up over there. What am I gonna read right now? 0, right? So I'm on 2 different legs. It looks like I'm on 2 different circuits, but in reality, I'm touching the same power source at continuity all the way back. So the difference in electrical potential between this point and this point is 0. I have 120 volts at both of them, but the difference in potential is 0. What am I going to read here? Now I'm reading through the resistor. No switches open.
120.
120, that's right. I'm going to read 120. There's no change. Still the same as what we did before. All right. I got a break in my load now. My resistor popped. What am I going to read now? 120. I'm still going to read 120, right? Because I'm still reading the difference in potential between these 2 sides. So a lot of people will ask me at this point, well wait, if I'm reading 120 degrees on a good load, or 120 volts on a good load, and 120 degrees on a bad load, how do I know that the load is bad? Anyone? Man, sorry, Ramon.
Resistance for amperage.
test it for amperage, or lock out, tag out, check your ohms. If you have a break in your load, you're not gonna read ohms. One other thing you do, stand there and look at what you're looking at. So a lot of people, we're looking at a diagram right now, but if you were actually there on site and you've got power on and nothing's happening, pretty good reason, pretty good explanation of why it's not working. We got a break in it. So at that point, when you see it's not working, what would your next step be? You just say, I got a bad thermistor, and then order a new one? What I would do is I would actually take it off the wall, disconnect it electrically, take it off the wall, check it with my meter. You'll see that there's an opening. And at that point, take it into the customer and say, hey, look, this is a resistive device. I put my leads right here, I got 0 resistance. This thing's definitely bad, I'll get you a new one. And walk out. They're gonna appreciate that you told them why it's bad instead of just, it's not working, let me rip it off and put a new one on the wall and charge for it. Here, I changed it up just a little bit more. I changed where the break is at. So now I broke my conductor back to my power source. What am I gonna read now? 0, yep. So how much power do I have right here? 120 volts, that's right. So if I stick my hand in here and grab this, even though I'm reading 0 volts, I come in here and say, oh, that's 0, and I grab that resistor, it's gonna be a fun day. Not really. So at that point, you're gonna complete the circuit somewhere, either to ground or back to the other side of the circuit. So we will read 0 right there. We have 120 degrees all the way up to this very point right here. 120 volts, I'm sorry.
Why you always check the ground.
Yes, exactly. That's one thing that I didn't have time to put on there, is that I wanted to add a few more slides where we come off and grab one side of our power source, and then explain how your readings are gonna be different from that point. Cover that for the next class. Okay, yep, so 0, and then the last one, we're gonna jump back on to something that we covered already. Ignore that lockout, tag out, that was supposed to be erased. So, if this were a device that has a DC power source, and let's say that this device monitors humidity, and it increases the current on this wire as the humidity changes. And it's putting out a 420 milliamp signal. But I have a controller that doesn't take 420 milliamps inputs. What can I do? I have resistors. So if I break the circuit, well, first of all, we're going to pretend like there's a load in this circuit, because if you don't have a load and you're running current, then you have a direct short. So for training purposes, we'll pretend like there's a load in the circuit now. If I were to measure the current going through, I would see the amp draw, 420 milliamps. My controller cannot read that. If I were to actually take this out and connect it to the input of a controller, is the controller connected internally in that input, or is it open? When you're actually looking into the input of a controller with a meter, it's actually open. You'll get you'll have a resistance there, but it's really open. So if it's open, can we pass current? No, we can't. So we're going to have to connect it to the controller some way or the other. There's no doubt about that. But we know if we open the circuit and connect the 2 leads, we're going to lose our signal. So right now, if I put my meter on milliamps, I'll read properly, right? If I put a resistor in there, what am I going to read? Just say this is anything, whatever you want. I don't care. If I put a resistor in there, I'm going to read the full difference in potential, right? Because there's no other load in there. So you got your inputs on your controller, right? Input 1, input, and your return. At that point, all we need to do is connect wires to the inputs. Your controller is basically just an electrical meter. It's no different than having 2 leads right here. The controller's got leads on every one of its inputs. And all it's doing is taking that meter and it's going to read your 1 to 5, 1 to 5 or 0 to 10 volt signal. So when you put this resistor in as a 250 ohm resistor, that's going to give us a 1 to 5 volt signal. and we're reading that difference of potential right here. So this resistor actually goes in right by your controller. And that's how you convert 4 to 20 milliamp. And we went over almost all why it works, and that's the how it works. Everybody follow that and why we do that? That's pretty much it. Don't let it be you. Anybody have any questions or like me to cover anything else in more depth? Pretty sure we're pushing time. No?
Can we see how many amps Andy got hit by? Average human by
Yeah.
1,000 ohms.
Never forget. Remember, free electrons are looking for a place to go.
Mhm.
Okay, for least resistance.
At the same time, whatever's connected to that pathway or that conductor, you think about it, especially with AC power, the pressure is changing, right? Pressure is changing. So that pressure is changing enough. At low pressure or low voltage, you can put your hand right on it, it won't hurt you. But the higher that pressure gets, the more chances those free electrons are going to push right into your body. And at that point, you're actually using your body and it's pushing electrons out of your body. And that friction we talked about earlier, of electrons passing through atoms, you're literally cooking the cells in your body when you get electrocuted. So, take care of yourself. Any other questions? Besides how many amps Andy pulls? Okay, so I'm gonna get ready to turn it back over to either Tom or John. But as they mentioned earlier, we're definitely gonna send out feedback surveys. And one of the things that I am most interested in are what you guys wanna see for future classes. So, look for it in your email. I'm assuming it's gonna come from Cindy. If you guys don't have any questions,
The guys are writing over there. Let's see if
we
they
might
have
have some
something.
questions from Omaha.
Uh-huh.
They just wanna keep you guys here.
Hungry.
Tom or John, would any of you guys like to add anything?
No, I said what I needed to say earlier, just that everybody's input after this class is going to be important, how we conduct future classes.
So, I just want to add, I do appreciate you guys being here. I know that this was repetitive and boring for a lot of you who already knew this information, but we would like to go this in-depth in all topics going forward. So if you give us your wants and desires and needs as a technician, we will focus on what you need to get trained better.
I guess I could probably take that a little bit further. That's up to and including kind of hands-on training with the products that we install. Maybe we put them back up next door so we can have hands-on training. So think of all those things and offer suggestions when the
Yeah.
survey comes out.
Hands-on training is definitely one of the things I want to get to. I want to get out of this boring stuff where you're looking at slides. Really, we want to have you walk up to a piece of equipment and start to learn how it operates and how you troubleshoot it. And what signals you should be looking for, how the inputs and outputs should be working, and how you troubleshoot what's wrong with it.
Alright, looks like we're good from Omaha. The guys was having some questions, but Carl helped them out and actually answered the question for them over there, so
Gotcha.
we should be good to go.
So I think either Fred or Mike had a sign-in sheet set up, so if you
Yes.
guys.
Yeah, we got them over
Anybody
there,
still
yep.
need to sign in? I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 people on the sign-in sheet. Coming back around now. Passing that back. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Other than that, thanks guys. Thanks for everything. And tear this food up.
Yeah, enjoy the pizza.